this is what a general workflow would look like. The first step is to establish the physics of the problem. You need to first list all the important phenomena that are present in the problem. For example, fluid mechanics is a given. On top of that, you need to see if there is significant heat transfer. And if the heat transfer is significant, it would again go as one of the important physics that governs the problem. The third would be something like chemical reactions. If chemical reactions are important, if the reactions are exothermic, if they are the source of heat generation in the problem, then they need to be accounted for as well. If you have say gas bubbles, and if you think that those gas bubbles are breaking up and coalescing to form a bigger bubble, then you need to account for that using suitable submodels. So before you go on to model your system using CFD, you need to properly understand the major physics that are present in your problem. Once you do that, and once you make some simplifying assumptions, like what to keep, what to ignore, you can start to see what would be the right approach for your problem. So this is when you think, okay, I would go with a Eulerian Lagrangian approach to solve my problem because my volume fraction is low, and my solid particles, they don't seem to be reacting or interacting very much with each other. So in that case, if your number of solid particles is less, if it's on the order of 50,000 to say a few million, then you can use something like a Eulerian Lagrangian approach. Once you do that, the next stage is to make your geometry and make the mesh for your domain. Once you do that, you need to make sure that your mesh is adequate. You need to make sure that the mesh that you decide to use gives you consistent and accurate results. And for that, you need to do this study called as grid independent study, where you would successively refine your mesh to make sure that your solution doesn't change appreciably. This is a well-established technique in CFD. So if you've taken any CFD course, you must have come across this, but this would be the next step in the process. Once you have the grid in place, you would choose the right modeling framework, and you would get your predictions from the model. If you think the model predictions are not satisfactory, you go back and you make sure that you refine your models, or if you think that certain physics of the problems were not well accounted for, you would account for that through suitable submodels, and then again you would solve the problem again in your CFD solver, which in this case would be ANSYS Fluent. And finally, if you get satisfactory results, you would make sure that your results are satisfactory by comparing your predictions against some experimental data from your lab, or from your chemical plant or equipment or whatever. If you don't have relevant experimental data, you would go and look for a suitable system in the literature and that you could replicate to make sure that your approach is well validated. Once you have a well validated, accurate numerical solution, you would post-process the results, and you would generate beautiful plots and graphs, and use that in your engineering calculations, right? So that is what you want. I mean, plots and graphs are one thing, but then CFD can tell you important things like the mass transfer rates for your entire equipment, or the peak temperatures that you might see in the equipment, which is difficult to measure using experimental techniques. So CFD will give you these important insights into the process.